lasted for 4 years. It began in 2017 and it ended at the beginning of this year. And we focused ourselves on new value chains in the area of polyester-cotton mixtures, but also 100% polyester and 100% cotton. Okay, sorry. Excuse me, I had some problems with my technology. So, the purpose of the project was, in fact, to use the existing industrial processes which we have in our region and to use them as much as possible in the circular economy. Without changing too much, so without investing too much, and try to use the apparatuses and the processes we have today. But of course, get acquainted with circular economy. The project had a budget of 1.6 million euro, and it was funded by IFCO FEDER. The main partners were Euromaterials. Leading partner was in Tourcoing as a competitive cluster, and the second part was CT2E, in fact. So also, maybe I should first say which region it was. It was the region of North of France, Hauts-de-France. It was a part of Flanders and also a part of Wallonie. So when I go back to the main partner, CD2E was the partner who was in fact responsible for the carbon footprint calculations. Then we have TCBL, well known meanwhile because it has been presented several times, and then Fedustria from the Walloon side because they had to give us the introductions into the industrial network. The associated partners were also for Wallonie BEFIN, which is in fact a company linked to SREW, and then also Resources, which is in fact a recycling cluster in Wallonia, which gave us in fact the raw materials, the end-of-life clothing, which we use then in our processes to recycle and to do the project. And then you also see UITENOR, which is the equivalent of Fedustria, but that in France, and also Team 2 and EcoTLC, also two French groups, let's say. When you are talking about textile recycling and textile recycling routes, then and you go down to the reality, to the industrial reality, you have three main routes to recycle your textiles and also your end-of-life clothing. When I say textiles, I mean industrial waste and also end-of-life clothing. You can have some chemical recycling, you can have thermoplastic recycling, and you can have mechanical recycling. Due to the fact that we were working in our region, being partly Flanders, partly Wallonie, and also the north of France, we didn't focus ourselves on chemical recycling because we don't have a Rotterdam or a Antwerp in our region. So in fact, we didn't have a huge chemical industrial infrastructure to use. What we used and what we did in our project was thermoplastic recycling and also in fact mechanical recycling, because there we have the industrial support. What we are going to discuss today and what we did mainly in RETEX is in fact the mechanical recycling of polyester-cotton blends of end-of-life clothing. We go into detail in this on this project. What we are not going to discuss today because the time is limited is 100% cotton industrial waste and mechanical recycling, but you can always ask me questions in the Q&A. And then we are also going to discuss and explain the thermoplastic recycling of 100% polyester waste, being or industrial waste or end-of-life clothing. We have done both. Let's start with mechanical recycling of polyester-cotton textile waste streams. Our industrial value chain, because the role of TCBL was in fact find the industrialists which are interested, bring them together, make them work together, not always evident, and then in fact make products. Make products that at the end of the day, with the existing processes, are in fact commercially viable. I mean technically viable, but also economically viable. So I mean really closing the loop and make things which you can sell. More very important also is that not only we wanted to use the existing processes as much and as far as possible, but we also wanted to have in fact a viable product, because we started from the assumption that when you want to have a recycling industry which lasts into the decades and into the future, you should be economically viable. And you cannot continue living on the taxpayers' money or all kinds of subsidies. You have to stand alone yourself without any external help. The industrialists which worked with us together were Van Moer, who delivered us the hospital clothing, which was in fact a hand-of-life clothing, coming from industrial laundries. This clothing was unraveled at Minot in the north of France, an unraveling machine where we made let's say the fibers, the basic fibers, which were baled and sent to RETEX-BEL, which made then yarns out of those fibers, and then also the fabric. And that fabric was then sent back to the same Van Moer, who made again hospital clothing, which was in fact okay concerning the technical specifications and also commercially viable. So in fact, it's a nice example, industrial example, not a lab example, an industrial example where you can close the loop correctly, let's say. Here you see what we used. In fact, we got from the industrial laundry, we worked with one industrial laundry, but we got all kinds of hospital clothing in our batch from several hospitals. You get trousers, you get vest, you get a vest with the hard, always with hard parts, of course, but the RFID tags with zips sometimes, with also all kinds of embroideries and all kinds of colored parts, with an average composition of, let's say, 2/3 of polyester and 1/3 of cotton. What we had to do, in fact, we worked with 2 tons. You see on the left-hand side picture the arrival of the 2 tons of, let's say, hospital clothing as such, right away from the laundry, and in fact, ready to be, let's say, treated. On the right-hand side, we removed then the hard parts. It's in fact let's say, in a social workplace, atelier protégé, they should say in French, where the people, in fact, we learn to people, in fact, to remove then the hard parts and, in fact, the RFID tags. I give here a few examples. On the left-hand side, you see all kinds of clothing. You have buttons everywhere, and every type of clothing is different. You find buttons on the most impossible places in that garment, and also RFID tags all kinds of places. Here, for example, you can maybe not see it. I cannot move I can move my cursor. You see here on the right-hand side in the pocket, for example, the RFID tag. We lost masses of time and also masses of money looking, in fact, where the zips were, where the buttons were, where, in fact, is the RFID tags were. Because if you want to have an industrial spinner spinning your fibers at the end of the day, he has to be sure there are no hard parts in your batch, because otherwise the spinning mill is going to be destroyed and you're not going to be in business. It's clear. So on the left-hand side, you see then, in fact, the clothing coming at the unraveling plant with the guy standing in the middle of the clothing. It's me. And in fact, it's ready to be unraveled. On the right-hand side, you see the unraveling plant with our colleagues from the partners, which we came at the end of the day, friends after 4 years at the Minot in the north of France. After unraveling, you have, in fact, the fluffy material, if I may call it that way, the fibers, let's say, and the unraveling was very soft. Very important point. We tried to have a good unraveling, and with good, I mean with a residual yarn length, fiber length, in fact, not yarn, fiber length, which was long enough, between 2.5–3 centimeters, to be spun again. And the spinner was present, so we adapted the parameters. Has to be until we got the good parameters to have the good fiber length. And as you can see on the left-hand side photograph, there are still some colored parts in it, in fact, because all the colored parts were not removed. And so we have to use it as it was. Right-hand side, it was built to go to the spinning mill. That already I explained. Maybe important to see to say here is that, in fact, when you unravel, you eliminate a big part of your cotton. Your cotton is dead. Your cotton has been treated, in fact, has been laundered in very harsh industrial conditions, which makes that the cotton is, in fact, not useful anymore after unraveling. And you see it on the right-hand side, for example, we have a lot of dust fraction coming from unraveling. And you're there, in fact, the cotton, it's very cotton rich. And on the left-hand side, the fiber fraction, which is going to be respun, is richer, and it will still become richer and richer in polyester. So you lose en route the cotton, which has to be replaced, in fact, once you are in the spinning mill. When you arrive at the spinning mill, in fact, we have spun a yarn. I am going to make a resume here because it was a long peregrination before we got there. But let's say we made a metric 30 number one end yarn, in fact, with 2/3 of polyester and 1/3 of cotton. And in fact, all the polyester is recycled, as I will explain you later. So in fact, it's more than 50%. In fact, mathematically, it's 67% of recycled material. All the PES, all the polyester is recycled, and the cotton, as I said, is in fact dead. Has been eliminated as dust. You find almost nothing back anymore. So you have to add virgin cotton to make, in fact, the yarn again. And that yarn has then been woven, and again, the hospital cloth was made and presented on the stand of TCBL at the Textile Fair of 2019. They call it their product Dr. Green, and it's a product now. It's in the market, they sell it. So in fact, it's a nice example of industrial circular economy, but no longer, let's say, lots of explanation, but a real product in a real market, which is viable because the company is continuing working on it. And I saw it recently, they still are using the same value chain as the one we mounted, let's say TCBL in the past, except the unraveler is another company. So to summarize the polyester cotton, let's say you have to unravel in a very soft way to maintain the respect of the fiber length. You have still to work with homogeneous waste streams because we made also lots of tests with domestic, let's say, end of life. I cannot discuss this here because it's then Jan has to allow me 1 more hour to explain. But let's say it's not feasible industrially today. You have to have more sorting. But let's start with the beginning. Industrial laundries are a perfect way to start with this process because it's viable. And let's say also with big companies, because company A is not going to wear the workwear of company B. So in fact, big companies can also be used as source for, let's say, source as for material to be unraveled. We also made an economic calculation, in fact, on the project to see if it is economically viable. I will go very shortly to it. In fact, what we have on the left-hand side is, in fact, the same process flow as I explained. You have the unit cost prices, you have the masses going in, the masses going out per step of process, and you see you're losing mass en route because, of course, in fact, you have dust, which is, you have removal of hard parts. You lose 30% when you remove the hard parts. You lose 15 to, in the worst cases, 25% at unraveling. And then when you start, in fact, spinning and carding and making the sliver, you are losing again 27%. So that makes that, in fact, you have a price of, in fact, 1.6, but it's hidden in my case. But on the right bottom side, you have a price of 1.63 euro per kilo of unraveled material coming out of our test. What we did, in fact, in the industrial plant is then make a sliver, because we made our calculation of cost price on the sliver level for the third metric yarn. We made, in fact, a combination of slivers, in fact, to make our final yarn then at the end. And it was composed of 25% of effiloché or unraveled material from RETEX, 25% of industrial waste coming from the spinner itself, which was in fact almost at zero cost because he reused his waste from his own spinning plant. We still had to make the balance of the 67%. We added some airpet from bottles, but this was all in fact a recycle. It is a recycle. It's or RETEX or waste from the spinning mill or bottles. The only virgin thing was in fact the virgin cotton which had to be added. And then, of course, when you make the calculations, you get, in fact, a positive margin of 7 gross margin on the sliver cost price base of 7.5%. I made also a kind of, quite theoretical calculation if on the influence of logistics, because we have to drive from A to B and from B to C, and then from C to D, and then from D back to A, maybe sometimes. If you eliminate all the logistics in your process, you gain 4 more, let's say, basis points in your margin. We also looked at, in fact, the influence, the sensitivity, the price sensitivity of the waste removal price. We got our laundry hospital clothing at zero. In fact, it was delivered to us at zero cost. But of course, if you start asking money for, let's say, the waste treatment, then, for example, you ask 100 euros, that's mentioned as minus 100 in my slide, then your margin is going up from 7.5 to 10.9, etc. On the right-hand side, you see also the price sensitivity on airpet prices for the airpet yarn, which is added to the sliver. to make your final product. And of course, when prices go down, you are going to be more profitable. And if you have bed price, which you have to add to your final yarn, is going up in prices, you start losing profitability, and you go out of business at 1,900. So the conclusions, in fact, is we have to work on homogeneous streams. We have enough laundries and industrial workwear to start working with, but it's end of life workwear. You have to, in fact, have more sorting research on, let's say, the domestic end of life. Of course, oil prices, which are very low, are always, in fact, hampering your profitability of your model. And we also made some calculations, but it's also subject not for today, on the incineration taxes and the incineration cost. It's not too far away anymore from the cost of just mechanically recycling. So deviate existing flows today is not so theoretical anymore. What are the next frontiers to go in full industrial gear is, in fact, to have machine builders who are adapted on their unraveling machines to, in fact, make a softer tearing process to have a better, longer fiber length. Our industrial laundries should launder in a less aggressive way, because then we can also recuperate a part of the cotton, which is now reduced to dust, because this is also a flow which could be then be very valuable and make your process even more profitable. And of course, removing hard parts needs more normalization, more eco-design, so that we can lose less time in removing them. We go to the second and last part of my presentation, and the thermoplastic recycling, but this time not of mixtures of polyester cotton, but just of 100% polyester, but of course also textile waste streams or industrial waste or end-of-life clothing. How did we treat them? Well, sometimes we have to prepare them in that sense that we have to remove the hard parts in the case of used clothing. Sometimes you have to purify, to clean something, and then in fact the first step is shredding or unraveling. We had also value chains and unraveling. Too long, not enough time to talk about it, but here we are talking about shredding or unraveling. You receive a fluffy mass. This fluffy mass is then compacted into pellets, and those pellets cannot be used right away. They have to be dried and crystallized, recrystallized, in fact, before you can put them into a thermogranulation line and make granulates. And then, of course, once you have the granulates, you can start extruding or make some injection molding. This happened at mainly the compacting, the granulation extrusion happened at the VKC, which is, of course, a daughter company of TCBL in Kortrijk. Here you have some photos of the operations, and in fact, you see the shredding plant, and then, of course, you're going to make fluffy fibers or flakes from it. Those fiber of this fluffy material is then compacted in a cow compactor, which is also standing at Kortrijk, in fact, and it's a very important step. This compacting effect makes pellets, and those pellets, you see them on the right-hand side, and those pellets has to resist abrasion. Now, the compacting stage is a very important stage industrially. First of all, it's a heat-producing stage, which is going to degenerate your intrinsic viscosity. So the cooler you can do it, the better it is. And then secondly, in fact, your pellets have to be compacted enough. They have to resist the abrasion in the next steps, because if you can do that, then in fact, you could eliminate, of course, drying and recrystallizing. You could eliminate this step, because now we have to pass through the compounding and thermogranulation, which is again a step which degenerates your intrinsic viscosity. So if you can eliminate this and go immediately to the extrusion, and we have done that with some pellets, then in fact you gain time, money, and also you avoid partly the degeneration of the intrinsic viscosity. You're going to see why I'm talking so much about that intrinsic viscosity in the next slides. We repeated that operations 8 times with 8 flows coming from 8 industrialists from the EU region in which we worked. And they are all all the flows are industrial waste, except the second one, which is end of life, let's say clean air suits and 100% polyester, where we had first to remove the hard parts. We didn't do anything with the pigments, we just used it as it was. What did we do then with the granulates of 100% recycled material, which we got in the way I just explained to you? We extruded them to make multifilaments or monofilaments, or we made some profiles out of it through injection molding. what did we see? In fact, that the results were not good enough for a industrial process, not good enough for a commercial viable product. Why? Because you have too much a reduction of the intrinsic viscosity, which in fact yielded a reduced processability, and also it was too brittle. Tensile strength of the yarns when we made them, I'm talking about the multifilaments, were not good enough to be processed later on. So we had to do something, and I'm not talking about the last 2 points because there are also from time to time problems. What did we have to do? In fact, well, we had in fact to add something. We had to add a real agent, what we call a booster, to upgrade the rheological properties, which we did, in fact, in several stages of our process. As I explained, we are starting from clothing, which we remove the hard parts if we have to. We make fibers out of it, but we shred them to have some fibers or pieces. And then we could grow the pellet route directly to the extrusion or make granulates, as I explained, and then, in fact, go to the multifilament. What we did, in fact, is on all those routes, in fact, is add some viscosity booster to see if we could then, in this case, make a better product. What we also did is, in fact, contact the compactor machine builder. And we made in Germany, these machines, new pellets, which were made in a more cooled way, in fact, so where we have a less reduction in the intrinsic viscosity. And in fact, as you can see here, our shredded fibers are at 0.67 decibel per gram intrinsic viscosity, and those compacted fibers normally were falling down to 0.5 through our machinery. Here we got 0.6, so almost no influence on the intrinsic viscosity, but these were the pellets coming from Karl, machine builder itself in Germany in his lab. So as you can feel already, machines has to be adapted to do that kind of process. And we made then some granules out of those compacted fibers, but we had to add that 2.5% booster, and we got a filament which was, let's say, processable on the machine. You have already seen several times on photographs and this morning, up to 40%, with up to 40% of recycled material. But I will cut a long story very short. This multifilament was not, let's say, commercially and technically good enough to go into the industry. As you can also see, the intrinsic viscosity is kept at a good level by the booster. Where we did succeed in our test is in fact in the monofilaments, where in fact with the same compacted pellets, let's say the cool compacted pellets, if I can express myself in a very special way, then there we got, let's say, good results with 40.7% of recycled material, 47.5% of virgin polyester, and 5% booster. There we could make a good monofilament. Here you see the picture with a diameter of 1.75 millimeter, and the composition I already told you, and it was tested out at Nefilatec, which is in fact a 3D printing company. The model, let's say the commercial model, is a Canadian company in Quebec, but they have let's say a French company in the north of France. That filament, in fact, has been tested on their industrial, let's say, 3D printing machines. On the right-hand side, you can see the YouTube film on our website, because, of course, like every project, RETEX has also a website. You will see it at the end of the presentation. And we could make, in fact, some products there. It was quite promising, let's say, in 3D. And again, we made the calculations on the viability of the process by, in fact, the same, let's say, the same logic, using the same logic. Where on the left-hand side you have the different process steps. You have the unit prices next column, and then the ins and the outs per step, let's say, and then of course the calculation per ton of recycled product. We were around the 800 euros per ton in the recycled product, polyester base per ton, and you have to compare that in the upper part of the slide. You see it. You have to compare it with, let's say, the RPET chips, because we calculated our cost price of the price of the chip of the granulate. Our 800 kilos has to be compared with the 1150 for the RPET and the 1390 of the PET virgin chips. And to be clear, those prices are dating from, let's say, the second half of 2020. But I can assure you today that the margin is even better now, because the RPET price today is now 1300 instead of the 1150 you see there in the top of the slide. And the 1,390, you made 1,450, 1,500 euro out of it today. So that means that in fact the margin you see there on the lower part of the slide, 343 euros gross margin profit on per ton of RPET is even today now 150 euros more than the 343. I didn't mention it for the mechanical recycling of polyester cotton, but all the figures I showed you in the first part of my presentation are today better. Notably better because prices of polyester and also prices of cotton have risen tremendously. Cotton, in fact, is more than 50% higher in price than last year. So, in fact, we are in an economical context today, which is certainly good. What we see here, in fact, is the price sensitivity on the booster. And then you see that when you go beyond the 2.5% of booster, in fact, because we use 5%. By the way, for the monofilament, at 2.5%, you're getting out of business. So, and that's for an RPET price of 11.50. On the right-hand side, you see the same calculation, but for a very low RPET price, 700, which was reality in the beginning of the COVID. And during COVID, the RPET prices were almost half. And then you see that, in fact, recycling is zero. It doesn't work anymore. Profitability is non-existing anymore. Here also the waste removal price, the same exercise as previously, where we see if we ask, of course, money for the removal of the waste we are going to increase to improve our profitability. I'm going to go a little bit faster because time is, let's say, pressuring me. So the conclusion, in fact, is that basically the compacting is a very important step where we should work on it, because then we eliminate the granulation for lots of cases, and that in fact makes the process cheaper. What we also have to see is low oil prices kill the whole thing generally, and in fact the booster price is too high. So that means in fact that in the next frontier, if there are some industrial priorities to be set, maybe we should work on introducing and installing more additional production capacity to make lower booster prices. And of course, in fact, because the best thing is in fact to avoid completely the booster addition, and that brings me back, of course, to the compacting step. And of course, the eco design of end of life clothing stays also. That makes me, and just to boast a little bit at the end of it's also a side project we did with Van Moer, Where to Go, Saint-Expel and Arcor. We also made some tests, in fact, in the dismantling of hospital clothing, but then with the Where to Go stitching yarn in the oven. What we learned there, in fact, has been used in the next project. It's called RETEX. My remembrance is good. Again, with Saint-Expel and Where to Go in a few other people, which I forget. And in fact, we learned several things there. In fact, one of the most important things was that if we want to be successful there, we have to have first a drying stage before you start irradiating the yarn. It's a very important step, because that allowed us to work in a much better way. And then you see again here in the social workplace where we made all kinds of tests in dismantling the yarn, the clothing. Sorry. I thank you for your attention. And on the upper side, you see the website www.dotheretex.eu. Thank you for your attention.